Hi, we're from the University of South Florida, and our class is Hardware-Oriented Cybersecurity and Trust, and our team members are Champagne, Derek, and Chang, and our project is on temperature and voltage dependent logics for output signal manipulation. For this project, we are presenting a temperature and voltage dependent digital design that can be used to control the functionality of the circuit output. For this design, we had to create two delay paths connected to an arbiter puff to create a race condition so that we could trigger our trojan. The two delay paths will race each other to make a rising transition. Depending on which delay path makes the transition first, the arbiter will either output 1 or a 0. To create our arbiter puff, we use LT Spice to create an RS flip-flop using NAND gates, and we use 6 inverters and 2 NAND gates to increase the delay path. Using the sweep function in HSpice, we are able to test our voltage stepping through 0.1 volts at each section all the way from 1 volt to 2 volts to see if our output was correct. For our temperature trojan, we use 6 inverters and 5 NAND gates to increase the delay path. To test the behavior of the environmental dependent circuitry under temperature changes, we increase the simulation temperature from normal temperatures of 25 Celsius to 100 Celsius by steps of 5 degrees Celsius each step using the sweep function also available on HSpice. To test our trojan, we are using an old Verilog project that we did last year. The project simulates an actual vending machine that will give out soda on a sufficient amount of cash when it's inserted. The conversion of Verilog modules to transistor-level netlists are done using the program called Design Compiler script from Synapse. The commands are presented on the screen. As you can see on the screen, the program has finished and we have our netlist. We also converted the trojans that we created in LT Spice into netlist so that we can inject them into the soda machine. We are now going to show you our temperature and voltage trojans being activated. On this figure, you can see that on the left-hand side, we have different values for where the temperature degrees are being activated at. In the picture, it shows that the signal remains 0 for normal operating temperatures of 25 Celsius, meaning that the trojan is currently inactive and will stay inactive until the temperatures reach a certain point. So at 35 degrees Celsius, as you can see, and the result will become 1. Now on the results of the voltage trojan, the output remains 0 during the normal operating voltage of 1. This means that our trojan is currently inactive and will stay inactive until the voltage has reached a certain point, which in our case is 1.1 all the way to 1.3. The results have shown that we successfully developed a temperature and voltage triggered trojans that can be implemented to actual hardware attack. This experiment has shown the attack results from two main functionalities of hardware trojans, which are to change the functionality and reduce the reliability. Both could be performed with our trojan implementations. If we connect the trojans to the soda output line of the FSM, we would be modifying the function of the FSM to give out free soda. On the other hand, if we connect the trojans to the coin insertion line, we can reduce the reliability by inputting a fake coin to get our soda.